talking about the multi-level intelligent waveform orchestration, a specification-aware framework for eliminating storage-debug trade-off. So the next 15 minutes, this infrastructure is going to enable you to make your agentic AI workflow more smarter in terms of both triaging as well as root cause analysis. So most of you could relate to this problem. So the FSDB waveforms that have been dumped and provided to you for debug, most of us doesn't even rely on 100% of the waveforms that have been dumped. So most of us spend only 5%, use only 5% of waveforms being dumped, and we neglect 95%. So capturing more isn't always capturing better. So we should have a framework that enables us capture only things that we need for debug, both for human in the loop debug as well as agentic AI debug. Okay, this is the problem statement. The static FSDB triggers that are going to capture waveforms for all of your test cases that are of interest in your regression. If it is going to be static, that's going to be blind. If there is a static triggering algorithm that looks at multiple test cases, some of the FSDBs generated out of it might be too large, some might be sparse in the debug depth, some might have missed the debug worthy window, and most of the waveforms are not even useful and we never look at it. The second gap is there is no multi-tier intelligence. So there is an absence of tier 1 that looks or creates a global policy that defines policy for your entire regression. So there is no cross regression memory. There is absence of tier 2, which is a real-time override that learns from your regression continuously and provides insights so that the next test or the test to be launched is learning from that dynamically. And there is absence of tier 3, which is cross-test learning across the entire regression. So fast tests cannot inform slow tests, even though the issues seen by them are similar. So the real-world impact of these static triggers are about 95% of the waveform duration or the number of waveforms never gets opened. About, I would say, quantifying it with a regular week-to-week regression or a day-to-day regression, we waste about 890 GB, and this also increases the debug productivity, brings down the debug productivity by 10x, and we find bugs later. Okay, the solution that I'm going to talk now is an orchestration architecture, wherein this talks about the end-to-end architecture involving all the 3 tiers and an orchestrator who's responsible for instructing all these. So on the top sits your simulation environment with the RTL design, the UVM test bench, the system log checkers, and the FSDB capturing engine. This is the multi-tier hierarchy, wherein that is driven by the central policy database, which has the capture policy that can be dynamically written by your human in the loop, real time, or by these AI agents in your automatic workflow. So the tier 1 is the global intelligence, which is the cross-regression memory, which learns from your previous regression, understands what the users or the team's priority before starting your debug process or dumping process before even your regressions are launched, plus dynamically gets updated based on the priority or the seismic issues seen. The tier 2 is an adaptive inference engine. It is per test, real-time, gathering intelligence from your simulation logs and from other FSDBs generated by the other test cases and driven by real spec event monitors, bandwidth checkers, and things like that. It has policy arbitration. It understands multiple modes in which it can dump FSDBs, and it has real-time override, whether based on learnings from the other test cases or based on user decision, and it writes back into the central policy as and when it finishes its inference. So the tier 3 is the cross-test intelligence. Within the regression, the peer test teaches the other tests which are still running or yet to be launched to precisely capture the debug window of interest. So this is across 3 time scales, 1 decision point from the orchestrator, and 0 simulation overhead. Okay, let's talk more about the orchestration and the FSDB outputs. So let's talk a bit about tier 1. This is the central database that I was talking about. This is governed by something like JSON or a text file, capture policy database for all your test case based on either a single test case of interest or a wildcard or group of test cases of interest. and it maps to different test patterns and maps to different FSDB modes. You can specify whether it would capture or always capture based on performance events, protocol events, or your custom test plan skills. And the tier 2 is about the dynamic on-the-fly detection. It can be bandwidth issues, power issues, protocol issues, or any event-driven issues. Examples like bandwidth degradation, signal watches based on some signals of interest, and it can be some performance counters and things like that. Tier 3 talks about the hint intelligence. This is a producer-consumer model wherein the cross-test learning happens. So the intelligent database, which is YAML in this case, works on the publish-consume model, wherein the publisher, the test case that's currently identifying issues that are debug-worthy, puts information into this YAML file. And the consumer, which is either a running test case or yet to be launched test case, can look at these hints and decide what is debug-worthy to be dumped. So this is orchestrated by the system-level FSDB intelligence orchestrator that is bound to the top-level test bench, consults all these 3 tiers every single time it needs, and turns on and off the FSDB, and the outputs are interesting. So a single test can never dump any FSDB, or it can dump 1 or more FSDBs based on the issues seen on the fly by these test cases. So examples are tier 1 can dump test name.fsdb that precisely surgically captures waveform of interest for your debug. Tier 2 captures only the bandwidth degradation based on the credit events or the bandwidth measurement events that it sees on the particular test case. And tier 3 based on one of the other tests that inform that, hey, I saw a bandwidth issue in the baseline test case, so make ready for capturing your events based on any other bandwidth events that you might potentially see, or back pressure events, or any counter events. Okay, when I was talking about specification matters the most, whether it's human who's in the loop, who's dumping these FSDB events, or the AI agents. So we have to specifically make sure that these specs are well written, and this is underlyingly governed by all several skills and model context protocols that infers information from the spec from the architects, test bench, as well as design architects, understands the protocol specs, performance specs, and clock specs. So for example, in performance mode, it understands the specifications from the architectural specifications on a particular traffic type, what is the expected bandwidth, and we have bandwidth events and monitors, scoreboards, checkers, and other live traffic traces that these engines can rely dynamically and make decisions either based on a sustained bandwidth degradation or dump it. You can even ask the FSDB to be dumped as a reference example for a passing test case for any other failing test cases debug assistance. So some of the examples of the tier 2 adaptive inference engines are like protocol modes, perf modes, full debug modes, and some of the test cases might need longer duration, even though the issues that were seen by one of the test cases used by the other test case, we might need to left shift the interval so that we capture the events prior to it, so that the tier 3 intelligence should be able to adapt and pick up information that the previous test cases might have missed, so that tier 3 informs the yet to be running test cases, and it can provide a longer duration for your quicker debug. Okay, this is how your approximate regression timeline looks like. So at time t0, the initiation phase happens, wherein the policy database is read. All the 3 tiers are launched and consulted by your infrastructure, and the pre-classification of the test case happens. So it can be either from your previous nightly regressions or your previous weekly coverage regressions. You can combine all of those and you can build your policy database, or the user can specify in his or her local regressions what they really wanted to dump the FSDB for, and approximately at 15% or 15 minutes of your simulation time, some anomaly might be detected. It starts dumping in waveforms on a surgical basis, not based on the entire duration of the time. And at time 30 minutes, a lot of correlation happens. The FSDBs that are being produced, the AI agent workflow that helps in mining the FSDB that are already generated, detects issues, updates the directory, or it can learn about clocking, reset, protocol, other issues, and update the central policy so that the yet to be running test cases can adapt quickly. And as I said, it understands the cross-test policy. You can also have a threshold saying that if you're running 500 test cases, if there are already 20 waveforms or 30 waveforms that have already been dumped, the whole purpose of this is to reduce the number of waveforms being dumped plus reduce the duration, right? So we have a strict cap on, hey, there are 5 reset test cases for which waveforms are already ready. No more dumping FSDBs for reset related issues. So these are the cross-test learning that can happen during this point in time. And finally, FSDB chunks based on the issues being seen are ready for your debug right when the test cases are ready and ready with the logs for your analysis. You don't have to rerun in any use cases. But in case there are events that are missed and the test case failed without FSDB, we have agentic AI workflow that looks at debugging the exact failed test case with the time of interest manually or in the workflow, and in the next iteration, the learning is passed on to the central database. Okay, so the results is pretty obvious. The more we engage these infrastructure over time in your regression database, in your development, you will come to a point where that you will have all the intelligence under which, signals under which your RTL or architects or design verification engineers will start their debug process. So it is 100% that precision will be guaranteed. We will be drastically reducing the total number of gigabytes wasted on the waveform dumping. Productivity increases significantly, and over time we'll see a lot of memory being saved. So the learning is compounding. When you start with a simple policy database, if you have 10 test cases, you don't have to run waveforms for all the 10. Just run it for 2 test cases of interest with your central data policy database. And as you scale the number of test cases and as you scale the number of different scenarios, your learning grows over time with all these multiple tiers interacting among themselves and post-regression inference as well. Okay, conclusion is again the results plus why this means we are debugging or root causing based on the specifications. If the AI agent workflow that your environment is going to adapt is also aware of the spec while dumping the waveforms, it significantly improves your debug quality, and this system improves over time. And the infrastructure is based on first principles with your system-level log monitors, system-level log modules that are bound to the top-level design, and these are multiple time scales, right? Like the more the number of hierarchies you add, the more intelligent your system becomes, and the coordination happens better. And it is universally applicable. It is not tied to any kind of a design SOC or IP. And the next steps are like right now the FSDB capture is done. So the next priority is precisely printing the waveform traces only for the power analysis or power estimation windows, and reinforcement learning based policy automation from historical regression database. And during the tail end of the project or when the coverage becomes the bottleneck, we should be starting dumping waveforms only that are coverage aware so that we are able to maximize the coverage closure process. With this, I will open the floor for questions. I think I went a little fast because I was watching the moderator giving me timelines. So these are some nice takeaways for every one of you to keep trying. A few snapshots of these slides, give it to your AI agents, your workflow, your environment. It should be able to come up with a very nice infrastructure for you to start playing with. But I'll finish this slide with the code. Every wasted gigabyte is a debug cycle stolen from an engineer. I'm not talking about tokens here, talking about humans in the loop. So thanks for your time.
Thank you,
This is really great presentation. I'm pretty sure people might have a question, but if I can hold my question. I have one question, which probably I can quickly throw since I can spend 1 minute. Anyone want to ask a question? If not, I'm going to take that opportunity and ask a question. So with this migration, do you ever see a situation where you enable FSDB dumping only for the failing simulation and not for the whole regression, just to save the thousands of gigabytes? Yeah, in general, like when we run hundreds or thousands of test cases, we don't dump FSDB for everything, right? So the main objective is the night regression when it's complete by like early morning at 7 o'clock. Say for example, a long running test case which takes 24 hours to run or like 23 hours to run. The next day morning when you open, if you have to rerun the test case, you waste another 24 hours just for capturing a little, right? So this infrastructure enables that you capture the waveform, not only for the failing test case, not the entire 100 GB or 120 GB. It ensures that for the same space, same budget that you have, 1000 GB say for example, instead of dumping for 10 test cases or 20 test cases, this infrastructure enables you to dump for 300 test cases or 400 test cases, precisely 500 megabytes each, right? You can either use AI workflow to make the debug, or even the engineers who are in the loop doing this debug, precisely when they open their waveform viewer, they will have the right signals of interest, RC signals, the debug nodes from all these infrastructure, and the duration for which the issues are seen. Good. Well, thank you, Vinod. I just wanted to clarify that part, but thank you. Let's move to the next.